So in the Butler-Volmer equation, this one, we have a parameter that is the exchange current. Well, the exchange current tells us how intrinsically fast is the reaction. So, how intrinsically fast is the reaction. Now, in a moment, we will see, for instance, how changing these terms from an analytical point of view, the Butler-Volmer plot will change. But before do this, it's important from an imaginary point of view understand what is the meaning of the exchange current. So let's consider our well-known example, for instance, the chopper. We have the surface of the electrode here, and we have the solution here. So, electrode and solution. We have here the oxidation, and we have even the other type of reaction. What is happening in this case is that we are when we are in equilibrium, we are in a situation in which the current is zero. And this speed is totally compensated with the same speed of the opposite reactions. And so the anodic current is compensated with an equal value of the cathodic current if the current is a function of the rate. And if the two rates are proceeding in the same way, also the current's contributes are the same. And the net total current is equal to zero. But what is important now is that in the moment in which we are moving away from the equilibrium, we can appreciate one of the two currents, or the anodics or the cathodics. It depends on the types of polarization we are providing. But in according with different type of chemicals and compounds and electrode nature, we can have different behavior. We can have different behavior that is quantified in terms of exchange current. What does it mean? That the exchange current tells us how intrinsically is the reaction. What does it mean? Tell us how strongly, when we are moving away from the equilibrium, the cathodics or the anodic current can sharply increase. Basically tell us if we increase a little bit the potential, if we apply over potential, how fast our reaction is able to go in terms of current with respect to another one. If we're imagining that maybe this situation is composed of one hand that goes in this direction, this hand that goes in direction represents maybe the chopper that is proceeding from chopper 0 to chopper 2 plus. From the other hand, we have the left hand that it represents the proceedings of the other reaction. So the passage from chopper 2 plus and chopper 0, the reduction. When we are in equilibrium, are completely balanced and we are not able to appreciate nothing. In the moment in which we are polarizing, for instance, positively, we want to promote the oxidations, and basically this start to become faster. And we have basically that is something that we are eliminating the reductions contribute, and we can appreciate the oxidation. But maybe if you're using another metal, another species, not chopper, we have always in the dynamic equilibrium, we have again a current that is zero. But maybe these two speeds are faster, are completely balanced, but are faster. We cannot appreciate nothing because the two different types of reactions are balanced in the same way, but are intrinsically faster. And in the moment in which we are eliminating one of them, just polarizing, the other one goes strongly, really more strongly. And so the exchange current tells us with the same potential how strongly one reaction is promoted in the moment in which we are going away from the equilibrium. equilibrium. So maybe for this metal, this situation is something like this. But for another metal, maybe the equilibriums involve higher speed intrinsically. And so in the moment in which we are eliminating one of the two contributes with a polarization, the reaction is proceeding faster with respect to another speed. So this is the meanings of the exchange current or the exchange current density. And from an analytical point of view, in the well-known Butler-Volmer plot, this literally means that higher the exchange current, higher the capability to reach higher current even with low polarization, with low overpotentials. And in fact, if the exchange current increases, we are obtaining something like this. So we are moving in this direction. So at the same potential, we can appreciate how the current increases if we are moving away from the equilibrium. So at the equilibrium, the situation is always the same, regardless the nature of the chemicals involved, since the current is zero, cause the overpotentials are zero. But if we are polarizing the electrode, since we want to move in an electrolytic cell away from the equilibrium, higher the exchange currents, higher the speed generated, even if we are moving away with the same value of overtension. And so tell us how intrinsically fast is the reaction in this way. Important is also the rule of the symmetry coefficient that basically tell us how much is promoted an oxidation with respect and reductions. For instance, we have this completely symmetry only when alpha is equal to 0.5, but when, for instance, is smaller, we have something like this. So we can say that the symmetry is simply lost. Or maybe when it's higher, we can even have something like this. So when alpha basically tells us the types of symmetry of our Butler-Volmer. So basically when we are proceeding with a polarization in this way, maybe here we can have a really strong promotings of oxidation, since alpha is high, so we are promoting a lot this one. Whereas when we are proceeding in the opposite directions, maybe promoting the cathodic current promote the reduction, since alpha maybe in this case is smaller than 0.5, we can appreciate how the current is really pure even if the overtensions are more important. And so basically this is extremely important. Now we have finished about the descriptions of the resolution of this function, imagining as the limiting step only the electron transfer, and we will see, for instance, in the last video, in the next video, the Tafel line and how the Tafel lines can be an interesting instrument in order to acquire the value of the exchange current, and only later we can start with the last descriptions in terms of symmetric, the mass transfer contribute to the overtension.